Hi everyone. In this tutorial, I wanted to show you how to route shortest paths along a graph, but using edge capacities. So I received a comment on one of the older videos on YouTube, which was doing the same thing, but with an older version of topologicpy. And the request was to have a Jupyter notebook to explain this. Now, that video, what it did is that it assumed there is a network, some kind of graph. Maybe it is cable trays or, pipes with certain capacities. And the idea is that you need to route several cables, several shortest paths along the same network, but you want those paths to respect the capacities. And if the capacity becomes zero, because there are, enough paths going through it, it should try to find a different path. So what you see on the screen is a representation of this. So I wrote a new Jupyter notebook. This is compatible only with the newest version as the recording of this video, which is version 0.9.0. And this notebook, which I will go through, is also available on the same topologicpy GitHub under the notebooks. And the file for the graph is called network.dxf, and I will upload it as well. So what you see here is the final solution of this problem. And at the bottom here is the original graph network. And the numbers represent the capacities of each edge. So for example, this edge here, this long here has a capacity of 2. This one is also 2. This one has a capacity of 4. Now, on top of this graph, you'll see, let's see, how many did we do here? 1, 2, 3, 4, 5, 6. So it found 6 paths. I think we asked for 7, but it couldn't find a path for the 7th one. It does vary from run to run based on which paths get priority. But basically, every path starts from the same location and ends at the same location here on the right. So you'll notice that for every edge, it only has the maximum number of edges of paths going through it. So if this is 2, it will only have 2 edges or 2 paths going through it. And you'll notice, for example, this edge here has a capacity of 3, but only has 2 edges through it. And this one here has a capacity of 3 and has 3 edges going through it as well. So it does respect the capacities, as you can see here, as well as here. So let me show you how I achieved this. So there is as I said, a Jupyter notebook. So let's go through it. So it's titled Tutorial on how to route paths using edge capacities. The idea here is that each edge has an assigned maximum capacity. When trying to find shortest paths for multiple pipes, cables, etc., the solution respects the capacity and also reduces it if it can be occupied. So every time an edge uses a graph edge or a path uses a graph edge, it reduces the capacity by 1. And I'll show you where that happens. Now, as usual, let me go ahead and restart here. As usual, the first cell you don't need on your own computer. This is because I'm using the development machine, because I need to tell it where topologicpy is. But if you pip install topologicpy, you should be ready to go. Here we import the needed libraries from topologicpy. So we need vertex. It doesn't look like we need wire. I think I imported it twice, so don't worry about that one. Cluster, topology, dictionary, and graph. So we import those. Now we need to have a DXF file. I have a file called network.dxf at this path. So you need to bring your own DXF file. The DXF file needs to be very simple 2D edges. I mean, it could be 3D, obviously, but edges only. And they should be connected on head to tail. So, or tail to tail or head to head. So, in the sense that you shouldn't have one long edge and then other edges going through it, unless you do more cutting and slicing inside topologicpy. But it might be good to have like the shortest span as a single edge. So here I have imported this. So now this is the main loop, so you have to study the comments in the code. So we have some imports here. So first of all, we get we have these topologies, right? So we imported these topologies. It's a list of topologies. So we're going to get all the edges of them, and we are going to flatten that list, because when you do this, you get lists within lists. So we go ahead and flatten the list of edges. Now we self-merge those edges, and we create a cluster by topologies, and then we self-merge it. And this is the final topology. It will clean up, it will deduplicate all the vertices, etc., etc. It should do all the intersections as well for you if they are not intersected, as I said before. But check your work, make sure the geometry is clean before you start. So now we get the vertices of this cluster. So these vertices are now deduplicated, they're unique vertices. And we have the edges here. They're already hopefully deduplicated. We could get them again from the cluster. If you worry about it, we should probably do that. So now we are creating a graph by vertices, edges. So we give it the vertices and the edges, and we create a graph. So all you need to make sure here is that your vertices and edges are all clean and can create a logical graph. Now, because the graph creates its own vertices and its own edges, it doesn't use these, it uses them but then copies them over, we need to get those back from the graph. So we say vertices equal graph.vertices g and edges graph.edges g. So now we have the vertices and the edges of the graph. Now, for this example, network.dxf, I know where the start vertex is, the coordinates of that, and the end vertex. So this is SV for start vertex, EV for end vertex. In your case, it will be different, or you might want to use different start vertices and end vertices for each path. I leave that for you to improve the code and change it. But for this case, I'm starting all 7 paths from the same point, and they all end at the same point. They just go on different routes based on the capacities. Now, this list of centers is just simply for display. It's completely optional, doesn't have anything to do with the algorithm. But in order to kind of display the centers nicely, or the capacities nicely, excuse me, I decided here to put an invisible vertex at the centroid of the edge and give it a label, call it 2, and here call it 4, whatever it is, so that it displays nicely and I know the capacities of every edge. So this is just the labeling thing. So we go through the edges for E and edges, and we give it a random capacity between 2 and 6. This is just for the tutorial here. Again, for your case, you will have to have the data associated with every edge somehow and apply it. So we create a dictionary by key value called capacity, and we give it this random capacity, which is a number between 2 and 6. We set the dictionary to the edge. So now the edge has the capacity. And now this is just simply for display, as I said, all of these lines. Basically, I give it a very small size, 0.001, so it doesn't show on the screen, but I give it a label which is a string of the capacity. And I set it to see the center, and then I add it to the list of centers. So you could ignore all of that if you don't want to see them on the screen. Right, now, this function here called edge filter, the nice thing about shortest path, graph.shortestPath, is that you can give it a function, a callable function, and it will call it on your behalf. It will call it with an edge to find out whether this edge should be traversed or not. Okay, so maybe you have a block, maybe there's a fire, maybe there's something on that edge that you need to tell it, no, if this edge now has an issue, you should not use it, and it will try to find a different edge. In our case, an edge should not be used if the capacity, if its capacity is less than or equal to 0. Usually it's 0, of course. We don't go into negative numbers, but just to be on the safe side. So if the capacity is 0, I return false. Otherwise, I return true. Now you might ask me, so how does it get the capacity, or how does it change the capacity? You will see it now in the loop, how every time we have an edge, we go through the shortest path and we reduce all the capacities by 1. And that naturally then makes this function work correctly. So it will check the capacity every time it's trying to find a new shortest path. So just bear with me. Just remember that, whatever you call it here is what you would give it as an edge filter input parameter for the shortest path here. And it will call it on your behalf. Right, so now we initiate a few things, or initialize a few things. SP list is a list of shortest paths, just all the wires. And we have decided this is whatever you would like. We decided that we have 7 paths that we would like to route. So for I in range 7, so we have 7 paths, we get return values here from the graph.shortestPath. So we give it the graph, we give it the start vertex and the end vertex. As I said, in this case, they are always, in those 7 paths, they are always the same, they don't change. And then I give it a turn weight of 0.3, which means that it will try to avoid turns in finding the shortest path. It will try to go in a straight line as much as possible. This can be anywhere between 0 and 1. So I gave it a little bit of a push, or an incentive not to turn. You can read the documentation on shortest path. It has become quite sophisticated in terms of trying to find straight paths. And as I said, I give it the edge filter so that it finds out whether an edge can be traversed or not. And I wanted to return the vertices and the edges. What this does is that it returns a list of vertex indices and a list of edge indices into the original graph list. So you can find out which vertices were used to compute the shortest path, what vertices does it go through, and this is a list of numbers, as well as the list of edges. Now, you are asking me, how do I get them? They're already here from vertices and edges. We got them from the graph. So you just simply use this as an index, and you can find it from that list. So try it out. So when you have return vertices and return edges, not only does the wire get returned, but a list is returned. That's why it's called return values. Now, if it cannot find the shortest path, return values will be none. So if return values, we actually have now a shortest path. Now we can get the shortest path itself, SP, which is the wire. The VI list is the vertex index list, and the edge index list. Okay. Now, in order to be able to see them clearly, I'm moving the shortest path by I plus 1 multiplied by 0.2, and that's why you see them here nicely stacked with a distance of 0.2 between them. And I append it to the list of shortest path. Right, so now it's been saved. So now comes the time to reduce capacities. So we go for I in EI list. Okay, so this is EI list that came here, the list of edge indices. We get the actual edge that it refers to, edges sub I, and we get the dictionary of it. We get the value called capacity, so dictionary value at key capacity. And if the capacity is greater than 0, then the capacity is reduced by 1. And then we set the dictionary value again. So we set the new capacity value back into the dictionary, and then we set the dictionary back into the edge. And that is immutable, or that is changed in place. So the next time it tries to do the graph, now that edge has a new capacity. And that's what edge filter will see the next time around, is this new value for capacity. So we went through the edges of the shortest path, and we reduced them all by 1. Now, this one you can ignore because we've done it up before, up and above. So now I'm just printing I plus 1, the number of the path. I'm printing the length of the path to see how it has kind of fared. And I'm printing the length of the wire here, and I'm saying meters. And then I will show it in the browser. That's it. I'll show everything in the browser. The graph, the centers because they have the labels, the list of shortest path, and the vertex labeled key is called label, and the size so that the centers don't show, etc., etc., so that you can see it clearly. So let's go ahead and run this. As you can see, it's very fast. Every time you run it, it might give you a different solution simply because the first path that goes through has priority and it can reduce the capacities as it wishes, and therefore the subsequent paths will have to find their way. But as you can see here, like in this case, for example, along this path, 3 is the bottleneck, right? So you can only have 3 paths here. And if it had more, it would work more. And here, of course, the bottleneck is 2, so you only have 2, so it can only do 5 paths. And if you go back to the output, you'll notice that it was only able to find 5 paths out of the 7. So 2 were not able to go through. If you run it again, let's see, this time it looks like we had 7. So now it found a better solution. And as you can see, it's taking different routes in order to reach the destination. So that's it. I hope you enjoyed this video. If you have any questions, feel free to contact me. Thanks again.